So when I lectured at Stanford last spring, there weren't nearly as many people.
These guys are all required to come, I know.
No. But that's because I'm not as interesting as our guest today, David Lobell. David is a professor, a new professor at Stanford University. He works on ecosystems, but he works on agricultural ecosystems and how they respond to climate and what sort of investments one might make to help productivity. One of the things that you should know, especially the first-year students, is that there's a process by which students can nominate people to come and speak. And David was a nominee from the student group for this colloquium. And then, of course, the colloquium committee asks, well, is there anybody here that knows him that can persuade him to come visit? And, and that's my role in this. So I served on a National Academy committee last year that David was a member of. And, you know, I thought he was pretty smart and he had good things to say. And at the time of our meeting in San Francisco, he was actually trying to decide among 3 job offers that he had for faculty positions at top-rate universities. And then one last thing to say before I turn it to him, because that's who you're coming to hear. David was elected just a month ago for one of the McElwain Awards from the American Geophysical Union. And these are awards given to you know, really outstanding young scientists at the beginning of their careers. It's restricted to people who are less than 36 years old. And when I was less than 36 years old, I wasn't nearly as productive as David has been. So, David, please, welcome.
So you can hear me okay? I was going to thank Jeff for inviting me, but now I realize I should thank the students for inviting me. I'll thank Jeff for persuading me to come. It wasn't a hard sell at all. I looked forward to the visit. I'm unfortunately teaching, so I had to squeeze this in. But I'm here all day and look forward to talking to everyone. Well, now that Jeff has raised the expectation. When BJ asked me for the title, of course, I hadn't really thought about what I was going to say or put the talk together. So I gave this hopelessly vague title of Towards Food Security in a Warmer World. But I didn't want to give a hopelessly vague and broad talk. So I'm going to be a little bit more specific and talk about crop responses to climate, which is obviously only a subset of this broader issue. I'll outline that a little bit at the beginning, but let me just say that I'm happy to take hopelessly broad questions at the end, and I'll try to make sure to leave time for that. Is it possible to dim some of these lights, or? Oh, you don't need to see me. I'm not much to see. I can see fine without the lights. Oh, I see the recording. Okay, never mind. Never mind. You'll just have to. Yeah. Okay. And now I got to figure out how to do this. So. Okay. Let's start with something I know you're all familiar with, or I hope you're all familiar with, which is the fact that climate is changing. In particular, climate is changing, and the inertia in the energy system and the climate system is such that we'll expect it to change regardless, really, of what we do on the emission side, and especially in the short term. Obviously, in the long term, out 30 or more years, the amount we decide to emit going forward is going to be really important. But there's a lot of technologies and infrastructure and emissions locked in that we expect to be warming at least at the rate we've seen in the last few decades for the next few decades. So this is sort of the starting point in thinking somebody like me who's interested in food security is what does this actually mean for agriculture and for food security, given that a lot of these changes are completely unprecedented in the history of agriculture. So we've been doing agriculture for about 10,000 years, and we haven't really seen globally these kind of changes over this kind of rapid time period. Now, from a food security perspective, of course, I don't care about the fact that temperatures are changing or rainfall is changing, but do the behind the back advance here. So The fact is that agriculture remains very sensitive, very responsive to changes in weather. Despite all of our great technologies and our modern capabilities, maybe that's me. That wasn't me, I don't think. We still are quite sensitive, agriculturally speaking, to weather. And so there is concern that even with a degree of warming, in many places you see as much as a 10% drop in production, and that's not even counting the other changes that go along with warming. Now again, from the food security perspective, that by itself might not be so worrying if we had plenty of food for everyone already, and this was just really a little bit around the margins. But as many of you, I'm sure, know, that there is this constant race really between global supply and even regional supply and demand of food. And so every little bit really helps or hurts in terms of what climate might do to production. And again, if you want to think about food security like I tend to and our group tends to, that in itself is not that worrying. There's a lot of people in the world who probably would benefit if food prices went up a little bit and they had to eat a little bit less. I'm not looking at anyone in particular, but that's the truth. The fact, though, is that, gotta find the sweet spot here. The fact is that in today's world, even with all the progress we've made, there's still about 1 billion people who are chronically food insecure, meaning that they, essentially that they often go to bed hungry. And I'll explain a little bit more technically about what we mean by food security. But the reality is that today we live in a world where we haven't made tremendous progress in reducing that number below 1 billion. And finally, even if you didn't care, say, about food security, and in some respects I came into this area really trained as somebody who was concerned about environmental science, concerned about what was happening to natural ecosystems around the world. And I think as a statement of philosophy, but also just as an observation of the world, that if you don't have food secure people, you're not going to have conservation in most parts of the world. You're going to have a lot of pressure on natural ecosystems. So even if even if you thought humans had it coming to them, they're going to pay the price, you still, I think, would be concerned about the situation from an environmental perspective. And there's also, of course, lots of complexities in what actually drives land use change and destruction of habitat, but I think food prices are certainly one of them, and food demand. So the question I want to talk about is, given all of these concerns from a food security perspective, how do we think about adapting to a warmer world? Now, to me, the real tough part is the following. One is that everybody talks about adaptation. Everybody says it's a good thing to do. But even more so than everybody talks about mitigation and thinks it's a good thing to do, there's not a whole lot of money behind this right now. There's not a whole lot of time spent actually trying to do this. This is just a nice, I think, figure from the World Bank showing their estimate, and their estimate has problems, of course, but just orders of magnitude, they say that in order to live in a world that's 2 degrees warmer and not more than 2 degrees warmer, it's going to take about this much money per year just to accelerate mitigation or accelerate low carbon technologies in the developing world. And it's going to take on the order of $75 billion in additional investments to help adapt the entire human enterprise, not just agriculture, to climate change. Okay, so these are rough orders of magnitudes about what the cost of dealing with climate change is going to be, both on the mitigation and adaptation side. If you look at the currently pledged funding for these activities, they're an order of magnitude smaller. If you look at actually, most of that is for things like energy efficiency, energy technologies. Very little of it is actually for adaptation. So we're down already to like $1 billion currently, and a lot less of that is actually for agriculture. A lot of that's for infrastructure, putting up levees, securing coastal areas. So we're talking about a big mismatch between the scale of resources that we would ideally like to have to deal with this issue and the scale that we actually have. Now, you could argue all day about whether this is just, whether this is right, but it's the situation. And I think, pragmatically speaking, there's a need to figure out what are the most likely investments that are going to work. What can we start with? What are the real needs, as opposed to everybody everywhere just saying, look at us, we need help, and we need money. And that's essentially what a lot of the governments and donor agencies are hearing. So we're trying to bring some capacity to identify the real opportunities or the real risk, if you look at it the other way. In agriculture, there's another specific, and this is not, I think you'd see the similar things in other sectors, but there's a very important point here that there's a lot of lag in time between when you actually try to do something and when you get something out. So this is an example here just showing you a study that looked at all of the historical research investments they could find and saw that it took about 20 years to really realize the benefits. This is a picture we took in Africa just to sort of give you a practical example here. They're developing drought-tolerant maize in Africa. There actually is some effort there. The Gates Foundation and others are pushing this. But even when you've decided you want to do this, you have to first, in this case, identify the characteristics of the crop that you want. You have to identify the varieties that have that. You have to develop the crosses to get that. You have to screen those at a wide area to make sure that they're stable. You then have to multiply seeds, which this farmer's responsibility is actually growing seeds for multiplication to distribute. Then you have to distribute them. You can imagine that each of these steps takes quite a few years. So if we're thinking about climate change 10, 20 years out, these are decisions we need to make now to deal with what we're going to see 10 to 20 years out. We can't simply wait and then fix it then. So this, to me, is the challenge that I wanted to talk about today, is how do we intelligently allocate scarce resources to adaptation, given that there are uncertainties, and given that both the uncertainties and our objectives may change going forward. So let me now just take a step because I don't want to assume anybody has sort of thought about food security before. You can basically think about three components to food security. There's the availability of food. Is there enough food in the world that if you divided by the number of people, people would have enough to sustain activity to get the right number of calories per day? So that we often talk about the pile of grain issue, like is there enough food? Then there's the equally important issue of if that food exists somewhere, does everybody have access to that food? Do they have the money to buy it? Do they have the land to grow it? Are they able to access that food? And then the third component that's often talked about is even if they have access to that food, are they healthy enough and able to digest the food and retain the nutrients? So a lot of this has to do with diseases, other interactions between things like diarrheal diseases and malaria and AIDS, and whether that really increases your need for food because you actually retain very little of it. So all three of these, if we start to think about climate adaptation, are potentially affected by climate change. So we have potential effects of climate change on diseases, not something I'll talk about today, not something I know very much about. We have potential effects on productivity, and importantly, this not only will affect the availability of food, the pile of grain, and the price of food, but it's really going to have a tremendous effect on people's ability to access the food. If you consider that out of all the billion food insecure in the world, about 3/4 of those live in rural areas, are actually very close to agriculture. Many of them are actually producing food, but they don't produce enough to sustain themselves. So they're net consumers of food is what we would say. But even though they're net consumers, their main source of income comes from producing the food. So if yields are depressed, if prices don't increase enough to help them, then you can see that it's going to have a very big effect on their income, either for negative in the case I just said, or positive if prices go up quite a lot. So you can already get a handle on some of the complexities out here in trying to track through what are really the risks, what are really the needs for adaptation. Now it's a field of complexities. It's a field of a lot of controversies or discussions or debates. My background is actually in math, and so I tend to get frustrated by this. So I appreciate the complexities, but as I was talking to somebody before, I want to find some way to actually ingest data into the problem, try to pick off a piece of it that you can make some progress on. And so if I were to summarize sort of my view of this problem, given all the complexities, start somewhere, choose some approach to trying to model these. If we can't model them, we can't really claim that we know anything about them, essentially. So we try to model them. We try to capture the main things that we think are important, some reliable but simple representation. And then we use these approaches to try to quantify what types of impacts we expect, what types of uncertainties are associated with them. And then I think a really key part of the modeling process is to delve into those uncertainties, and that's what I'll talk about today. Understand what they're really arising from, what really are the opportunities to reduce those uncertainties with new data. So I'll really talk about each of these steps today. And I just wanted to point out that I think any good modeler will realize that once you've chosen an approach, you've made some important decisions that you should eventually go back and reevaluate. The climate model community is quite good at this in comparing different models, but it's no different here. A lot of my work is trying to compare different approaches. So what I'll talk about today is one type of approach, but there are some others. You can feel free to shout out questions or throw things at me if things aren't clear. Again, just one more introductory slide here is that I'm certainly aware that climate change is by no means the most important or the main driver of food production or food security going forward. There are tremendous changes occurring in agriculture, as there always have been. There are tremendous changes occurring in people's livelihoods and in development, as there always has been. And so oftentimes these debates, I think, get bogged down by these discussions of, well, you forgot about this, well, you forgot about that. And the point is, we haven't forgotten about these things, but we have to pick off pieces of it, try to put these pieces back together. And if I were to spend 45 minutes just talking about the pieces that exist, I would be done. So let me tell you about one piece that exists and how we actually try to make traction, to get traction. So I'll really talk about just this piece of it today. How is climate going to affect crop productivity throughout the world? So obviously, this question is not something that's very new. I think when people started thinking about climate change initially, one of their first reactions was, what does this mean for food production? So there has been a lot of work on this in the past. Let me just point out a couple of the features of the work that make it less than ideal for doing this kind of work. One is that initially there was really questions designed around, do we even need to care at all about climate change? Is mitigation even an issue? So they were typically looking at like 100-year projections, very simplified, often just doubling CO2, saying what happens when you double CO2 to food production. So the timescales really aren't in line with the types of timescales we think about when we're talking about decisions today about 20 or 15-year investments. So timescales are too long. Oftentimes, they're focused exclusively on the crops that are traded globally that are important to the U.S. economy, things like corn and soybean and wheat. And as I'll show in a second, throughout the world, these are by no means the only players in food security, especially in certain parts of the world. So there's a big gap there in terms of crop coverage. There's also a huge gap in terms of spatial coverage. If you look at one of the most influential and important studies that was done about 16, 17 years ago, Africa is basically represented by a couple of simulations that were done in Zimbabwe. And then basically things are interpolated. As you can tell, these are the actual points where they ran crop models. You know, this was the state of the art at the time. This was a good study. But it certainly leaves a lot to be desired. If you want to say what are the priorities within Africa, for example, this is not going to get it done necessarily. And then finally, there's a very, I think, rudimentary treatment of uncertainties in a lot of the literature, which is true in a lot of climate impact literature. And so you're left often wondering, well, was this just a particular model, a particular result, or do we really have enough information here to make some definitive statement about what the risks are? It's just to give you a sense of that, which is a figure I made out of some of the studies that have been done for different countries in Africa for maize projections by 2050. And you can see, depending on the study, and even depending on different runs within a study, you see huge ranges going from, say, -20 to +20%. And so, you know, if you imagine yourself a policymaker looking at this stuff, it doesn't give you much confidence, I think, in the state of knowledge. So, okay, so let me just talk a little bit about sort of bringing you up to speed and then talk about some recent work. So I started in this area, I don't know, a few years back, and the initial question was really, okay, what regions should we be really focused on? What are the big areas that are very sensitive to climate change? So we did an initial assessment, sort of very rough, kind of along the lines of you use the axe before the chisel. We were just sort of taking a very rough cut at what the global scene looks like in terms of threats to food security. So we did essentially three simple things. One is to just say, out of the hundreds and thousands of different combinations of places and crops that are grown, what are really the ones that people depend upon for food security? So obviously there's a geography to food security. There's a geography to crop production. So where should we actually be looking if we want to really focus on food security? It might be very different than where we look if we want to focus on corn prices. Second, for those given regions, what can we learn from looking historically at the data in terms of how sensitive these crops are to weather? And then third, once we have that information, what can we understand about future risks, feeding these models or having these models look at climate projections and then using these to project what's likely with 20 or 30 years of additional climate change. So just to give you a little sense of this, for the first step, this is just a summary of actually the sources of calories in different regions of the world. So in Asia, for example, you see a huge importance of rice and also wheat. But in Central Africa, for example, you see a huge importance of cassava as a source of calories, or sorghum in the Sahel. Not news to anybody who does food security, but this is just to help us lay out what are the major crops we need to consider in each region. So we're not necessarily going to consider rice in Central Africa. We're not going to necessarily consider sorghum in South Asia, et cetera. Then the second step I mentioned was trying to map historical data and understand from that data how things respond to crops and climate, how things respond to climate. So there's a million ways to do this. Let me just say briefly that I think one of the limitations often of past work has been that they haven't had actually very precise definitions of what they mean by weather that the crop is seeing. So in other words, a lot of economists will go into a region and look at average annual precipitation or average annual temperature and try to relate that and make conclusions off of that. So that's one thing to be concerned about a little bit. And then also you have big countries where the crops are only grown in a portion of the country and people are looking at large-scale averages. So essentially what we did was first try to take care of that by looking at specifically where the crops are grown and specifically what the months were that they were grown. And we just did a weighted average basically of the observed temperatures and precipitation by month. So we can weight over the growing season months and then weight spatially. So we come up with each crop in each region or each country, depending on what scale you do it at, of a time series of say, temperature or rainfall throughout the record. And then we take that data and we look at the reported harvest data. And this is just kind of some examples. I'm not going to, again, go through this in very much detail, but you can see that this gives you a sense of the flavor. So you can see crops that depend a lot on rainfall, like rice in South Asia. You'll see a very positive correlation between rainfall and yield. You'll see a weaker negative correlation between temperature and yield. Wheat tends to be more heavily irrigated in this region. You see less of a rainfall response. You see, again, this weak temperature response. So again, this data doesn't scream confidence at you. There's a lot of scatter here, but we can propagate this uncertainty that's due to this scatter, and we can see if you do that, can you still make statements about how different risks compare. So the way we propagate that uncertainty, not only in the crop data, but also in the climate projections that we're using, because as you know, there's lots of uncertainties there too. We use a fairly simple Monte Carlo approach where we have a simple linear model. So the change in yield is really the change in temperature times some sensitivity parameter and the change in precipitation by some sensitivity parameter. You could do fancier things like square these and interact them. And we've done that, but it doesn't qualitatively make much of a difference in most cases. In some it does. So you take the crop data, you take the certain climate model, and you combine these, and you feed in the climate model values of these, and you feed in the crop model values of these, and you come up with a projection. Then you resample the data, you resample the GCMs, and in a simple Monte Carlo approach, you come up with the distribution of impacts. So that's going to be our way of capturing uncertainty. And you end up with some distribution of impacts that looks like this. And when we do that across all these crops and regions that I talked about, you get a map that looks like this, where we're showing just for the top 5 crops in different regions what the impacts are likely to be. And you can see that there's a lot of uncertainty in general, but you can pick out that there are certain places like South Asia where consistently a lot of the important crops are negative. You can see in South Africa there was some very big increases that we projected. And then in other areas like West Africa, things were a little bit more ambiguous. So that's sort of the starting point here. This is sort of an initial pass, as I said. We've chosen an approach, we've made our projections, we've looked at uncertainty, but we haven't yet gotten really into, I think, how do you reduce that uncertainty? We've done the first step, which is important to quantify uncertainty. If you can't quantify uncertainty, your projections are not very useful. So that was the first step. So this was sort of where the story took a little twist, because I was curious about why do we have such huge ranges in these projections. Take the worst case of southern Africa, where wheat and maize were projected to have big impacts, but we're on the range of 10% to 50%. And as I should have made clear, this is just out to 2030 relative to 1990. So over a 40-year period, you're talking about changes that would really make a lot of these areas not viable for maize production. Why do we have so much uncertainty? What is really driving that uncertainty? It came out of our analysis, so we should be able to say what our analysis is doing to provide that uncertainty. So if you look at the sort of our initial thought, and I think what a lot of the conventional wisdom would be, is that it's driven by precipitation. Because if you look, this is just showing for each region that we looked at. It doesn't really matter what these say. Don't worry about that. If you look at both wintertime in blue and summertime in red, and this is just showing you the distribution across the different GCMs. So you take, say, 20 GCMs. There's a value for each GCM, and this is just showing you the median value, the interquartile range, and then the extremes. Okay, everybody with me so far? So precipitation, as many of you know, according to the GCMs, is very ambiguous in terms of its direction of change. Different regions. Some get wetter, some get drier. There are exceptions. For example, Eastern Africa, almost all the models show it getting wetter in December through February. That doesn't mean all the models are right, but by our technique of trusting those models, using their spread as some measure of uncertainty, that's what they show. Temperature, on the other hand, everywhere is getting warmer, right? You see everything's warming by a degree on average. There are some models that in some regions go as high as 2 degrees. There are some that go as low as half a degree. But they're all warming. And this is the conventional wisdom in agriculture is precipitation, we don't know the direction. We know it's warming. That's not an issue. But we need to know the precipitation direction if we're going to tell you what happens to crops. So that was sort of our prior, let's say. Okay, so if you think about it, what we can do is just decompose this variance or this uncertainty into the 4 things that we don't know. The response to temperature, this one, this one, this one, and this one, right? We could actually fix each one at a time and change all the other 3s, or we can fix 3 at a time and change the other 1, depending on what type of measure you want to use for sensitivity or uncertainty. In fact, because this is such a simple linear model, you can actually do it analytically. Using just a standard formula for the variance of a product is essentially it expands into 3 terms for this temperature, which is the expected value of the sensitivity squared times the variance of temperature. So this term is really inheriting the uncertainty from the climate model uncertainty in temperature, but scaled by the sensitivity to that temperature, expected sensitivity. Then this is the inverse, so you have the expected amount of warming squared times the uncertainty and the coefficient, and then you have the interaction term. And you have a set of 3 similar terms for precipitation. So 6 terms will add up and give you the total uncertainty, this sort of range here. Okay, so everybody's with me still?
So when you're doing this, you're assuming that the response is linear?
We're assuming that the response is linear for this approach, right? We can make other assessments where we don't assume the response is linear, but it would be more difficult to decompose, but you can use other techniques. Yeah, so it's a good question. The nonlinearity of any model and of, say, when you're modeling crop responses to weather depends a lot on the processes you're looking at, but also depends on the range of values that you're considering. So here we're looking at fairly marginal shifts in temperature, things like 1 or 2 degrees. And so for most crops in most regions, a linear model is a pretty good approximation. If you're using models that look across, say, a big range of space. So here we're just looking through time at a region. With those scatter plots I showed you, it was just a time series analysis. If you're looking at between areas that are 10 degrees and areas that are 30 degrees, you definitely need something that's nonlinear because you have to capture the fact that crops have sort of an optimum temperature and optimum rainfall. But all this to say that if you use those quadratic terms and everything, for the range of data here, it doesn't actually make that much of a difference. So let me continue and And unless, was this just a follow-on to that, or?
I was just going to ask you, is there a reason why you didn't include variables of irrigation or flood or drip?
Yeah, so there's a whole suite of variables that affect crop production, definitely. There's also a limited data record here. And so you run into issues of model complexity. You always pay a penalty by adding a parameter that you might not be able to calibrate. In this case, what we're doing is we're looking at changes in yield due to changes in weather. So in a sense, we're making some implicit assumptions here that other things remain static, or at least that if they're changing, they're not changing in the relationship between temperature or rainfall and crop production. But this is really just looking at the partial derivative of crop production over a very narrow range of changes in temperature and rainfall. That's why we feel comfortable with this. And as I said, we can test this and see that it actually reproduces the results of more complicated models. So here's what we get when we decompose, when we compute each of those 6 terms and look at how they add up, what fraction they contribute to total variance. So I've just color-coded these here, and I've shown you for the top 20 crops in terms of global food security. So the most important crop by our measure, most number of people who are most food insecure, who get their most calories from that crop, is rice in South Asia. And you can go down the list if you're interested in what the most important crops are. But what surprised us is that almost all the variance in a lot of these regions is driven by temperature terms, and not at all by precipitation terms. There are certainly big exceptions and important exceptions, like up here. But our expectation was that everything would look like this because the direction of rainfall change is uncertain. And this, in a sense, shows you the value of doing this analysis because you can actually confirm, or in this case, refute what our initial assumptions were about what was driving the variance. Now, when you think about why that is, it's actually, in hindsight, like most things in hindsight, quite clear, is that you have a trend in temperature that is very much larger than any of the historical variation that you're dealing with. And you have a trend in precipitation that's actually not all that large. Another way of saying this is that we don't know the direction of rainfall change true, but we also know that it's not going to be plus 50% over the next 30 years, and it's not going to be minus 50%. All those models I showed you were often in the range of negative 10 to 10%. And if you compare that to, say, a model that differs in warming by either half a degree or 1.5 degree, then that's the comparison you need to make. And then if you think in that space, actually a degree of temperature can be a lot more important than a 10% change in precipitation. So this is just showing you the trends as a fraction of variability historically. So a lot of the projected trends in mean temperature change are on the order of 2 to 3 standard deviations of what historically has been seen. And precipitation, which we are conditioned to think is so important. I mean, every report you see about crop failure is due to drought or rainfall. They say that even if they don't know, but a lot of times it's true, and that's because year to year, that's what's driving a lot of the variability. But if you look at the trends, they're actually quite small and often within the noise of historical variability. Another way of saying this, or another manifestation of this, I think, is that if you look historically, this is just, for example, the time series for this #1 crop, rice in South Asia. You look historically at the temperature trend, and you look historically at the rainfall trend. Up till now, this is not necessarily the best proxy for what's going to happen in the future, but it's a reasonable one. You see that temperature trends relative to variability are much more important. A caveat here is that maybe we've just underestimated the sensitivity to precipitation, or maybe the climate models are underestimating the uncertainty in precipitation. A lot of people think that they're really all not sensitive enough. There's been some reports that rainfall has changed faster than the models are actually showing in terms of global average. There's some people who say, well, within the errors of the data, it's not actually true. But even if I grant you a factor of 2 in terms of the underestimating the uncertainty in precip or underestimating the sensitivity to precip, you still are in a situation where temperature is driving most of your uncertainty. Another thing I've looked at to try to understand whether this is really just an issue of model projections being too conservative in rainfall is we've been looking recently at just mapping out what the changes in temperature and precip have been for major growing regions. So this is just showing you for maize. And interestingly, the US hasn't seen a whole lot of action in temperature, and this is maybe reflected in the complacency of farmers in the US to climate change. But if you see throughout the world, in China, in Europe, in Brazil, for all the corn growing regions, and it's a similar story for other crops, you've seen this dramatic increase in temperature if you express it in terms of multiples of the historic variability, year-to-year variability. Precipitation, this is showing you the same scale, and you can see that very little falls outside this range. So most of these trends are kind of what you'd expect just by chance and are not as significant in terms of distinguishing it from natural variability. So a little counterintuitive at first. In hindsight, maybe not so much. This is just a histogram of this previous trends I showed, just stuff we've been working on recently, where on average, for all these crops, most areas are seeing something like a 2 standard deviation increase already in temperature. And most places are seeing, on average, something like a 0 change in precip. Of course, you have some places that are seeing big increases or big decreases in precip. But actually, if you fit sort of a null model here, it's not that different than you'd expect. Not, again, to say that climate change doesn't cause rainfall changes, but just that if you think from a crop's perspective about what's going to drive variability, it's surprisingly secondary to temperature in our view. So this is sort of newfound respect for temperature at least led me to 2 things. One is to think about, well, how do we do better at narrowing that temperature uncertainty? So rather than think about narrowing uncertainty overall, let's focus on that temperature sensitivity. We could also focus on trying to get the temperature projections right, but that's tricky business. You get into a lot of issues, and there are a lot of people working on that, but I'm not really a climate scientist and not doing too much on that end. But there is something we can contribute. If you go back, which I won't try to do because I'm not very good at this thing, you would see that the sensitivity of crops to temperature is actually, in many regions, the biggest source of uncertainty. So how do we make progress there is one issue. And then the other thing we've simultaneously been thinking about is how do we reduce that sensitivity to temperature most effectively? How do we get so we've been talking a lot with the crop development community about their focus on climate adaptation. They're starting to think about it, but like most people, they're starting to think about drought. How do we understand, first, whether they're even thinking about temperature? Second, what are the options on the table? What are the points of progress to make, and so forth? So trying to engage more in that conversation as we continue to understand things. So what time do we go to? Okay. So I'll leave time for questions, I promise. So what this has led me to is actually one project I wanted to talk about today, and there's a couple others. But this is a project that is using a very different approach than we used before. So before, we were looking at time series analysis of country-level production compared to country aggregates of monthly temperature and precipitation, and all the issues associated with that. What we've done here is actually teamed up with an organization called CIMMYT, the International Maize and Wheat Improvement Center, who have coordinated for the last decade trials around the world. Just their normal business is creating varieties so that when, as I explained before, they have to test them very broadly. So they have coordinated trials they have a lot of partners in this with national programs, and they screen varieties to see how they're doing and to see which ones do well at a large number of places so they can identify which ones they should be releasing. They don't care all about climate change when they're designing these experiments. But the fact is they have all this data, and even though they haven't collected any weather measurements, we can intelligently try to recreate what the weather was that happened there. We do have some sense of it. Not the best in a place like Africa, but we have some sense of it. So can we merge these data sets, which are an order of magnitude bigger than what we had before, an order of magnitude finer in terms of spatial scale, which gets us some advantages and some disadvantages? Can we leverage that to try to improve our understanding of crop responses? So can we? This is a figure just showing you in red, blue, and green. And don't worry about the colors. These are all the places where they've done these trials. So mainly Eastern and Southern Africa, and a few along the west. And the gray dots here are showing you the weather stations that we have data for that we have to interpolate from to get to the station where we actually want to recreate the weather. So there's some interpolation that goes on here. And there's an enormous amount of cleaning and digitizing of the crop data that's taken quite a bit of time. So I'm going to skip over that, but for the students out there, recognize that these things often take a year to just compile the data sets to look at. So once you do that, you get something that looks like this. So I don't have the sample sizes here, but there's something like 15,000 trials here. Let me explain one more thing, which is that conveniently for us, not at all because of us, but conveniently, they actually test these varieties under normal rain-fed conditions and then under imposed drought conditions, because they really want to see, as I mentioned before, they have a drought-tolerant program. They really want to see how crops do when they're really stressed. So what they do is pretty clever. They grow it in the dry season with irrigation so that they're sure there won't be any rain, and then they cut off irrigation and impose the exact amount of stress that they want to, or they try to, and see how the crops do. So we have those trials where they've imposed drought. It's obviously a more expensive thing to do, so there's fewer samples of it. And then we have sort of the run-of-the-mill screening trials that are grown in the rainy season with ample rainfall or the typical rainfall. So we have two classes here that we're going to analyze separately. On the left is showing you the run-of-the-mill rain-fed experiments, which is about 15,000 trials that we have. And here showing you the drought, where we have something more like 2,000. This is just a scatter plot of the data to give you a sense. So 3 variables here: yields, average temperatures, and then days above 30 C. So days that are quite hot, about 85 Fahrenheit or hotter, which we've known from studies in the US and elsewhere might be especially important for crops in terms of explaining why they go south in years that are really hot. So a scatter plot of the data shows you a couple of things. One is that you see actually a huge amount of scatter due to all of the many things that we talked about affects actual yields. But you also see sort of an envelope that shows you, I think, to very first approximation what the effect of temperature is on yields. That you have an optimum temperature. You have a very nonlinear response where if it gets too cold or too warm, they're not very happy. What I was saying before, just to revisit it, is if you're looking at a country that spans, say, 22 to 24, you can get by with a linear model. If you're looking at a whole range of data like this, you can't get by with that. You can also see that, luckily for us again, or maybe we can take credit for this, but I don't think so, that average temperature and days above 30 are correlated, but they're not hugely correlated. So there's some hope that we can distinguish, actually. Is it really the days above 30 that matter, or is it just the average temperature that matters? Very difficult to do with the types of data we were working with before. On drought, you see something different. This is actually a good illustration of why you don't just look at scatter, because as we mentioned, there's tons of things different about different trials, different sites. And typically how you model these is you have fixed effects for each site and each year that account for things that are not in your model that you're worried about. Like this site might have better soil. This site might have better management or higher fertilizer rates. Things that we don't actually have data on. So we just have to say, let's give this site its own intercept, basically. Let's assume that they're all responding to temperature the same, but they might be at different levels. And that, in fact, is, you see with drought, you sort of go down, but there are a few sites that are hot, but they're also high yielding. Now, this may be telling us that temperature is not as important in drought, or it may be telling us that just there's a lot of fixed effects here that we have to get out. So the statistics will tell us which of those two are true, but this is just to give you a sense of the data that we have. One thing to notice here is that with the drought trials, because they're grown in the dry season, you actually have a lot more exposure to really hot days, whereas we had very little relative exposure to hot days. So in some sense, this is going to be, even though it's a much smaller data set overall, there's a lot more opportunity to identify the effects of extreme heat. I don't actually, okay. I can't really see very well, but I think we're okay. So this is just jumping a little bit to after you analyze the data with fixed effects, with stuff that we don't have to get into, but it's a fairly simple standard econometric technique of data analysis. You see that the effects of average temperature, which are shown here, or a very highly correlated measure, which is degree days between 8 and 30 C. There are some effects. Under optimal management, there's some slightly positive effects. Under drought management, there's some negative effects. But you see that the real action is out here, is how frequently you're above 30 C. Now, the reason we see an effect with average temperature, if you think back to the previous stuff, is because, of course, as I showed, average temperature, and this is highly correlated. If you don't have this separately in your model, this is going to pick up a lot of the explanatory power. So it's not that these models are wrong and that they only have average temperature, but they're sort of using a pretty blunt instrument to get at what really seems to matter, which is days above 30. So you can see, interestingly, that the drought trials have actually about 50% more sensitivity to extreme heat than the optimal management trials. And right now, we perceive this to be showing us that the effects of heat depend a lot on the water status of the crop, not surprising to any physiologist, but one of the ways, for example, that crops deal with heat is to try to transpire more so they can cool down their local temperature. And if they don't have access to that water, they're not going to be able to do that. So again, these are air temperatures that we're using, not sort of the micro meteorological temperatures, and the disparity can often be due to the water status of the plant. Okay, so if we take these relationships now and we try to say, okay, if you add temperatures now to these sites, what's going to happen? What I've done here is computed that and plotted it as a function of where the site was in terms of the baseline temperature. So you go here from very cool sites to very warm sites. So for the cool trials, if you add a degree, what do you expect? Well, you actually expect that that slight bump from average temperature wins out because they're really not even seeing any days above 30 C. So even if you warm them a degree, they don't get there. So you actually gain about 10%. And you see the 95% confidence interval is fairly narrow. You start moving to warmer and warmer sites, and you start hitting temperatures above 30 C. So if your average temperature is 23, it's very likely that you're spending some of your time above 30 C. Okay, so this would be something like where the US Corn Belt would be, somewhere around here, although it spans a huge range. And then as you get warmer, you start to see a real dominance of that strong negative effect because you keep seeing very hot days. Drought is a different story, interestingly. Even at cool sites, you're losing because even average temperature increases don't help you if you don't have water. If you don't have water, any sort of heat, this is sort of speculation here, but any sort of heat really makes water even scarcer, increases evaporation, so you're really not in a position to deal with heat if you're water stressed. So this is now, if you then look at the temperatures that are distributed around Africa, this is just showing you every grid cell. Obviously, some areas grow maize and some don't, but this doesn't have it masked out. Showing you on the top what we would predict if it was under optimal, what we're calling optimal rain-fed management, and here if the drought conditions that were imposed in those trials were present. So of course, because these are trials, they're not actual farmers' fields, so we don't really know where farmers lie in those spectrums. So this is sort of bracketing the good water status, bad water status scenarios. And you can see that the cooler areas, like the high altitude areas, even throughout much of southern Africa where we saw these huge decreases, there is some increase up to a degree. So you see that. But there's also a lot of areas, here. I'm showing here, the mean, and then these are sort of the uncertainty estimates, the 5th and 95th percentile. You see a lot of blue areas, you also see a lot of red areas. If I were to mask out, which I should have done for this plot, most of the current areas, a little bit more than half, about 60%, are in these red areas. So if you looked at the current maize areas, if they were grown with ample water, about 60 or 65% of them would be hurt by warming of a degree, and the rest would be helped. But if you look at drought conditions, as I said before, they're pretty much all hurt. Actually, the point of this slide I wanted to make was that now we've narrowed down our uncertainty quite a bit. We still have this problem of not being able to relate it directly to farmers' fields, but we have this model for what happens under certain management conditions, and you can see that the uncertainties are quite a bit more narrow. And in a sense, these are not very distinguishable. If you look at the extremes here, red areas tend to be red both in the low and high extreme. And this was pretty clear up here, too, that the 95% confidence interval was on the order of 5, or let's double it and say 10%, much narrower than we had before. So to me, this was a nice thing to see after spending all that time putting the data together, that it did help us to understand temperature a little better. Okay, so with that, I'm going to stop and say there's really two things that you could take away, or you could choose one of these if you want, or you could choose half of one if you want. They say that people only retain 20%, so I usually try to put 5 things and you can choose one. But I only have 2 today. One is this notion that I think we have to re-examine a lot of our bias towards thinking about year-to-year variability when we're thinking about what's new about climate change, how do you adapt 20, 30 years down the road. I think temperature is where a lot of the action is going to be. Sounds kind of simple to say global warming is going to be a lot about temperature. But in the agricultural community, there's been a very big emphasis on rainfall with very legitimate sort of, I think, historical reasons for that. But I think it's important to understand just how important temperature is in driving impacts. And as a more general point, it's sort of a theme of my research, and in this case too, that I think new data sets are out there. There's a lot of opportunity to make progress, and I think that the sort of steps I outlined, where you first quantify your uncertainty, then understand it, and then attack it in a sort of efficient way, is going to be really fruitful for a lot of areas of impacts research, or a lot of areas of environmental research in general. There's just such an explosion of data out there. And this is really, I think, just one example of a type of data set that had nothing to do with the question, but just, and has a lot of issues with it, a lot of noise in it, but just has sample sizes that are just, for somebody who's trained in statistics, the sample size is just too appealing to turn away. And I think that there's a lot of cases like that out there. So with that, I'm happy to take your wild and crazy questions.